Hi everybody, welcome back. In this video we're going to be taking a look at one of the most important results in all of Calculus 1, which is something called the fundamental theorem of calculus. And as you should expect, anytime you have something that has the name fundamental theorem on there, seems like that's going to be a pretty important result for us. By the way, a theorem is something that's been proven in math, so not just do we think it's true, but it's actually something that we have a rigorous proof for why something works the way that it does. Okay, so the fundamental theorem of calculus actually has two parts. You'll notice I put the statement of the first part of the fundamental theorem at the top of this page, but it does say part 1 on there. There's two parts. And with this result being so important, this is probably going to be split up into a few different videos. So in this video, what I'd like to do is just look at the statement of the result, look at the statement of the fundamental theorem of calculus, and try to understand what does this mean for us, or why is this so important for us. And then also in this video, I want to look at what are some of the background results that we need in order to prove the fundamental theorem of calculus. Okay, because a second video that we're going to have is we're going to actually prove why does this result work the way that it does. Okay, anytime we have a result that's this important, it's really good to look at where does this come from and why does it work the way that it does. Okay, and then after that, we'll probably look at some different examples, probably in a third video there. Okay, so the first thing we're going to look at is what does the statement of the fundamental theorem say, and why is it important to us? Okay, so you can kind of read this at the top. It says if f is continuous, we're assuming f is a function. If f is continuous on a closed interval from a to b, then the function g that's defined by g of x equals the integral from a to x of f of t dt, where a is less than or equal to x is less than or equal to b, is continuous on a to b and differentiable on ab, the open interval from a to b, and g prime of x is equal to f of x. Okay, so let's try to make some sense of this statement here. Okay, first of all, it says f is a continuous function on a closed interval. Okay, now notice it doesn't say f of x at the top, it says f of t, or it doesn't even say f of x or f of t, it just says f. In this case, we're going to use f of t as the input because I want to just make a distinction that this t is different than this x up there. So we're using t as the input here, but just think about that as being a different kind of an input variable. We have a closed interval from a to b, and so I want you to think about a picture, first of all, that starts at a and goes up to b. Okay, and somewhere on this interval, we're told that x has to be between a and b. And this is a picture that we're going to look at when we see the proof in the next video. But what I want you, the reason I'm drawing it here is because I want you to remember something about what this integral means for us. Maybe you've seen some things somewhere else about how an integral and an antiderivative are somehow related, but we actually don't know that yet. In fact, that's what this result is going to tell us. So for now, the way I want you to think about an integral, and maybe you've never seen that before, that's fine, that's what we're going to get from this result. What I want you to think about with an integral, every time you see this integral notation right here, you should automatically be thinking, after what we saw in the last couple of videos, the last couple of sections, you should be thinking about area under a curve. Okay, area under a curve or area under a graph. And so when we talk about the integral from a to x, I'm really talking about this area right there from a to x. Okay, so that's an important thing. And so basically we have a function g that's defined as an integral. And then the bottom line here actually gives us properties about g. If we define g in a certain way, then what we actually see is that g is continuous on the closed interval from a to b. G is differentiable on the open interval from a to b. And those are both really good, but the most important one for us is going to be this last kind of statement there. What we end up getting is that if we define g in this way, then g prime of x is equal to f of x. Now, this is really interesting because g is an integral, right? G is defined as an integral. So g is an integral, and g prime of the integral, okay, so I'll just say g prime of x is the function f that we started with on the inside of the integral. Now, I know on the inside of the integral it says f of t, and this one over here is f of x, but they're the same function f. just with different inputs. And we'll get into a little bit of the detail there. But g is an integral. G prime is the function inside of the integral. Essentially what this is saying is that g prime, the derivative there, kind of undoes the integral. Okay, that's kind of a really informal way to talk about the result here. But if I could kind of simplify this or kind of put it in layman's terms for us, kind of I'd say the informal result for us, or the way to kind of word this so that just kind of the common person can try to, or who knows about derivatives and integrals, can try to understand. The informal result basically, and this is a huge result for us, is that integrals and derivatives are essentially kind of undoing each other. Okay, integrals and derivatives undo each other. That's kind of the main idea, okay, from this. Here's another way to say that. You remember talking about antiderivatives at this point, and you should have talked about, we talked about antiderivatives, about how you can undo a derivative and kind of think about working backwards. And really another way to think about this is that it says that integrals basically are antiderivatives. Okay, so this is kind of nice because if we're trying to find the area under a curve of a really complicated graph, we don't need to try to kind of guess or try to use geometry the whole time for things that get really, really messy. We tried to do some of that in the last section, but we could only do it with shapes that worked really well. Now what we're going to find is that even if you don't know how to use geometry to find the area of the curve, or I should say the area under the curve, you can use antiderivatives, and that's essentially the same thing. Using antiderivatives are the same thing as the integral. So this is going to be really important for us because it gives us a great way to be able to undo antiderivatives or use antiderivatives and say, what does that mean in context? Okay, so this is a huge result for us. So we're going to prove this in the next video. Now before we do that, I want to take a look at some past results that are going to really be necessary for us. So let's say past important results that are needed in order to prove that this fundamental theorem of calculus works the way that it does. Now let me just say this. There's a few different ways that you can prove the fundamental theorem of calculus. These are past results that are needed in order to prove it the way that we're going to prove it in the next video. So this is one of a number of ways that you could actually prove it. This is what our book does. I like this result. I think it's a little bit more rigorous than some other results or some other proof techniques. But in order to do it, it involves looking at 3 different past results that we've seen so far. And I tell you what, I'd say that we've seen all 3 of them. We actually haven't seen all 3 of them. We've only seen 2 of them so far. Okay, but do you remember in the last video that I created where we talked about integral rules that are kind of properties of the definite integral? I said there's another rule coming up. And so that's one of the 3 rules here is kind of our last property of the definite integral. In fact, our book calls it property 8 of a definite integral. And so that's going to be one that we're going to need here as well. Okay, so first one, and some of these should sound familiar, but the first one we're going to need is something called the extreme value theorem. I hope you remember the extreme value theorem. We'll talk about kind of what, I'll remind you about kind of what does this say and when might this be useful. But we have already seen this in our past, so we're not going to go into a ton of detail. I just want to remind you of this one to say, hey, we're going to need it in the next video. Property number 2, or important rule number 2 that we're going to need, is what our book called property 8 of integrals. Okay, now we didn't actually look at this one in the last video. I think we went up to property number 7, and then I just said there's another one coming up. So this is going to be with this last one. And then the third past important result, we got to reach way back from our past. By the way, if you want to look up where the extreme value theorem came from, that was in section 4.1 in our book. And then the last one is going to be one of your favorite old results that you might remember from, oh my goodness, so early on in the course, like a few weeks into the course, if even, back when we talked about limits. And so maybe one of your favorite results, I'm being a little sarcastic, but one of your favorite results from back then was called the squeeze theorem. Do you remember the squeeze theorem? from a long time ago. I know for us in our book, this was section 2.3, and we didn't even look at chapter 1. So this is like the first 2 weeks of class, basically, was talking about the squeeze theorem. So we'll look at what all of these results say, and we'll see, and then we'll kind of get into why are they needed. Okay, so let's start with the extreme value theorem. I've put the statement here, and here's what it says. Okay, so we can just kind of read this. You might remember talking about this at some point. It says if f is continuous on a closed interval from a to b, sound familiar? That actually is kind of how the fundamental theorem started out, by the way. If f is continuous on a closed interval from a to b, then f attains an absolute maximum and an absolute minimum. Here's the idea. If you start out with a and b and you have a function that is defined on that closed interval, means you have endpoints. Okay, you have a lower endpoint and an upper endpoint. And so somewhere this function has to have an absolute minimum and an absolute maximum. Now the minimum could be somewhere on the function, like if I draw a little bit of a different function in here, this function right here has an absolute minimum that is somewhere in between a and b. It's like right here. That's just this specific example, but it has to have an absolute minimum somewhere. But the absolute maximum or the minimum could have also been on an endpoint. And remember, that's why we needed a closed interval. If we have an open interval, this doesn't actually work, because you could have an open interval where you have a vertical asymptote and then there is no maximum. But if you have a closed interval from a to b, then you have to have an absolute maximum and an absolute minimum for the function on that interval. Okay, this is the second result that we need. Okay, the second result says this. It says if little letter m is less than or equal to f of x, which is less than or equal to capital letter M. Let me draw ourselves a picture for a second. Let's say we have little letter m right here, capital letter M right here, and basically we are told that f of x has to always be between those. Okay, this was the result that we didn't actually cover in the last video, but I said that it was coming up. Let's look at the integral. Let's look at the integral from a to b of f of x. The integral from a to b of f of x is the area under the curve. Remember, area integrals are talking about areas right now. And if you look at the area, I'm going to go ahead and change color here a second. If you look at the area here, this m times b minus a, that is the area of this rectangle right there. And so clearly the area of this rectangle right here has to be less than the area, or it could be equal if f of x is just a straight horizontal line there. Has to be less than or equal to than the area under the curve of f of x. And go ahead and change color one more time. This capital letter M times b minus a is the area under this rectangle right there. And so clearly if you look at the area under that rectangle, that area has to be bigger than the integral of f of x from a to b. But notice m and m, little letter m and capital letter M, these are constants, okay, constants. They are not function values. But basically this says that if you have a function that is bounded like this, has a lower bound and an upper bound, then its integral is also bounded, integral from a to b. Okay, so that's kind of the picture that goes along with that. Again, we're going to use this result in our proof as well. Last but not least, one of your favorites from earlier on in the semester. Do you remember the squeeze theorem? The squeeze theorem relates three different things, three different functions in this case, but if you kind of relate it back to what we just saw on the page before, you might kind of be able to tell a little bit, foreshadowing about how these two results are going to kind of work together a little bit. But the squeeze theorem basically says that if you have f of x that's down here and always lower, and h of x that's always up above, and somewhere g, I guess let me use a different color for g here, g is somewhere in between and has to be in between these, then if f and h both have the same limit, so maybe here's a, and f and h both have the same limit there, and it doesn't have to even exist, it could be a hole in there, but g basically has to have exactly the same limit and go to exactly the same place. Okay, remember this one from your past? All three of these results are going to be important in our next video as we prove the fundamental theorem of calculus. So go ahead and jump on over there once you're done with this one. Hope you enjoyed.